Welcome back to the APECE Yukon Chemistry Chapter 6 homework review with Mr. Bwilkosz. We're checking out problem 43. For problem 43, you're asked to give the symbols of the elements that have specific requirements or recommendations met. So for 43 part A, you are asked to find things that are in period 2 with empty 2p orbitals. So we're not going to look at the first period, we're going to look at the second period. And it asks for things that have empty 2p orbitals. So lithium and beryllium would both have empty 2p orbitals because at their ground state they would not fill the 2p. They would not have enough electrons to actually need to fill the 2p. And technically, if you're asking for empty 2p orbitals, I think boron would also count because it would have two empty 2p orbitals with its only one electron in the 2p sublevel. For part B, you're looking for symbols that are metals in period 3 with at least one unpaired electron. So in period 3, we're considering right across here 11, 12, 13, 14, 15 through 18. So sodium is a metal, and it would have one unpaired electron. It would have an electron in the 3s1, but magnesium would not, because it would be 3s2. Those two electrons would be paired in the s sublevel of energy level 3. Aluminum would also count as something that has an unpaired electron because it would have it in the 3p. It would be 3p1. When we get to silicon, phosphorus, sulfur, chlorine, and argon, those aren't really metals anymore, so they're kind of out of the mix. Part C, we're looking for an alkaline earth metal with filled 3D sublevels. So alkaline earth metals are things that are in this group 2 right here, alkaline earth metals. And in order to have filled 3D, they need to be past this part of the periodic table where number 30 is. So everything that shows up after 30 but also shows up in this column right here counts. So after 30, number 38 strontium, number 56 barium, and number 88 radium all count. Number 8, we're looking for a halogen with unpaired 4p electrons. So it's got to be in this group to be a halogen. If it's got unpaired 4p electrons, that means it has to have electrons in the 4p, so it needs to be filled in this region of the periodic table. And bromine is the only one that actually applies to that. If we go past bromine, they would have any elements that we would consider that fit as a halogen would have a filled 4p and therefore not have any unpaired electrons. Let's take a look at 49A and D. In 49, we're again writing electron configurations, we're writing ground state electron configurations. So we have our Aufbau filling order here, right here, and we have our periodic table to help us find. So we've got magnesium, you find on the periodic table with 12 electrons, that's where this 12 electrons come from. And we're considering also an ion of magnesium, 10 electrons, it lost it to become Mg2+. And then we also have tin 2+, and tin 4+, so we find tin on the periodic table, there it is, number 50. So with tin 2+, it lost 2 electrons to become 2+, is 48. Tin 4+ lost 4 electrons to have 46 electrons. And then it's just follow your filling order. There are some exceptions as to when electrons get lost, but usually it's the ones on the highest energy level, unless you can manipulate the ending of a particular electron configuration to make a full or half full outside energy level. But in this case, you fill pretty much in order. Regular magnesium fills to 3s, needs to lose 2 electrons, become Mg2+, the ion of magnesium, and you don't have a 3s there anymore. Those 2 electrons have gone, presumably, to Kansas. For tin 2+, it loses its 2 outsidemost electrons right here. Those would be in the 5p, if they were there. And then for tin 4+, it will lose the 2 electrons in the 5p, but then it'll also lose these 2 electrons in the 5s. Let's take a look back at the next problem, number 51, just part A. 51 part A, you were asked to find how many unpaired electrons are in the ion mercury 2+. So you write out its electron configuration, and mercury shows up in a position on the periodic table in this range right here, number 80 or so. And so it's going to lose the 2 electrons that are in the 6s to become its ion. And then you'll notice that every single orbital we have is filled, so there are 0 unpaired electrons in this particular ion.